Welcome back, students. Here we will be doing the derivation for moment of resistance. So this is the same diagram we will be using for the derivation which we have already done to derive the value of K for both the cases. So it's a simple beam section with width B and effective depth D provided by AST, that is area of steel. N is the depth of neutral axis, and this is the stress diagram where compression is shown, compressive force is shown, that is capital C, which is acting at distance n by 3 from the top compressive fiber, and capital T tensile force acting at A from compressive force. Okay, so now what is moment of resistance? As the name suggests, it is the resistance towards the movement by the beam. So it is the ultimate movement which a beam can resist, beyond which the beam will fail. Okay, so this is the maximum moment which can be taken care by the moment, after which the beam will start yielding or beam will start failing. It will show some cracks, or it may collapse, or it will deflect, and it will not work according to the to our requirement. So moment of resistance is denoted by MR, M suffix R, MR. So to start with this, as we know that there is no resultant force acting here. Since there is no resultant force across the section, the total compressive force is equal to the total tensile force. Okay, so here total compressive force we are going to calculate, that is capital C will be equal to capital, sorry, so total compressive force C will be equal to T, that is capital T. Okay, therefore moment of resistance, that is MR, will be equal to the moment of couple consisting of compression and tensile force. So it is the moment of couple, basically moment of couple. So we will see what is the total compressive force. Total compressive force C will be equal to area of stress triangle multiplied by the width or the length where it is acting. So this particular compressive force is going to act for the full section. So here the area is half into base into height. This is the area of the stress triangle. We will substitute base and height later. And when I say width of where it is acting, is this compressive force will be acting for the entire width of the beam, right from this section to this section and from neutral axis to the top. So it is basically the width of the beam. So here it will be equal to B. So what is the area? What is the base? Base is equal to C, or you can consider it as KD, and height is C. So it is half C into KD into B. This is from the stress diagram. Can kindly refer to the stress diagram. And this will act, this particular force will act at n by 3 from top. Okay, we have already marked this distance n by 3 in the diagram. Now we'll write what is total tensile force. So total tensile force, that is capital T, is nothing but T, that is the tensile stress, and it will act for the entire area of steel. So T into ST, and this will act at distance small d from top of the beam. So we measure this distance from the same top compressive fiber. So it is at n by 3 for the compressive force. Again, if you want to see the diagram, it is n by 3 for compressive force, and from here it is equal to d for the tensile force. Okay. Now, if we have lever arm, that is the distance between C and T, compressive force and tensile force. Lever arm A is written as J times D. J is some constant which we are going to derive. So this is the distance between the compressive and tensile force. We can write this as, we have A is equal to J times D, which is equal to D minus KD by 3. Right? So, here this equation can be written as D into 1 minus K by 3. This is from the diagram. From the stress diagram, we can also write this distance A as D minus KD by 3. Again, I'll just go back to the diagram. See here, this is A. So, from the diagram, it is D minus this n by 3, and where n is KD by 3. KD. Okay. So, we can write this A is equal to J into D, where it can be written from the diagram D minus KD by 3, D taken out as common, it is 1 minus K by 3. Therefore, this J can be written as 1 minus K by 3. Right? So, if J is 1 minus K by 3, A will be equal to J times D. So, we have D here. So, J becomes 1 minus K by 3. Or the critical value for J is 1 minus Kc by 3. So, this is the equation for J from the diagram. Okay, is this clear? So, now what will be the moment of resistance? What is moment? It is nothing but moment is equal to moment of resistance, that is Mr, is equal to load or force into perpendicular distance. This everyone knows, it's common. So here it is Mr will be equal to, we can write two equations for this, either compressive force multiplied by the lever arm, or we can write Mr equal to the tensile force into the lever arm, where lever arm is equal to A, right? Therefore, if I write the first equation, Mr is C into lever arm, I will substitute the value of C from the previous equation that we have already derived, that is half C into KD into B. Okay, so it is half into C into KD into B into the lever arm, that is J times D. So this is equal to, I can just take all the constants out, that is half C into K into J, and it will be here BD square. Just rearrange the equation and you will get this. Now this can be written as capital R BD square. So again I am using the constant R to consider all these constants, that is C, K and J, where what will be the value of C? C we can write it as sigma CBC, that is the stress in concrete. So here again I will write where R is equal to half sigma CBC into K into J. And MR is equal to RBD square. Okay. If we write the second equation considering the tensile force, that is MR is equal to T into lever arm. Both are possible, so I will just write here or. Okay. Here T is T into AST and lever arm is J into D. Okay. So I've just substituted the value of capital T, that is small t into AST, into lever arm is J. This also can be written as T will be sigma ST in our case into AST into J into D. So here we will get the equation for calculation of area of steel, which is equal to MR upon sigma ST into J into D. So when we say that we need to design a beam, basically we need to provide the amount of steel considering the moment that is acting and the dimension of the beam. So now just when we talk about designing of the beam, when we talk about the design of the beam, what we have to do? The first is we need to fix the dimension of the beam. Once we fix the dimension, we need to see what is the load that is coming onto the beam or onto any section. Now due to this load, there will be the side effects. What are the side effects of this load? Bending moment, shear force, torsion, and there are many more. Okay, so for beam it is bending moment and shear force. So for bending moment, we provide main steel. We provide steel and concrete to take care of the bending moment, and for shear force we provide steel again in a different form. You will at least learn this as we go ahead. So now in this working stress method, what we have done, we have derived 4 constants. First is M, which is modular ratio. Then we have K, which is the neutral axis depth factor. Then we have J, which is the lever arm factor. And after that we have R, which is the moment of resistance factor. So to get the value of R, we need J, we need K. To get the value of K, we need M, that is modular ratio. And to get the value of M, we need sigma CBC, that is grade of concrete. Okay, so once we get what is moment of resistance, that is MR in kilonewton meter, this is what you have already studied in structural analysis, calculating the moment for different type of beams and for different type of loading with different end conditions. After this, for this particular moment, we will provide the amount of steel in mm square to resist the moment that is developed. This will be our designing of any structure. It's very simple. Okay, so now first we will do some numericals only depending on the constants and calculation of MR. Then we will go for designing and providing of AST and detailing the AST. Okay, so here is a small derivation for moment of resistance. Kindly go through the notes that I have already circulated and also go through the video to understand the moment of resistance in a better way. Thank you.